Hello, my friends. We have already done a great job, 3 days of our school. Of course, the most part of this job has been done by 3 people. And today is the first day. As always, Manju is first, as always, because he lives in India. And Elizabeth always finishes because she lives in America. And somewhere in the middle, Germany, where Zahar lives. So please, Manju.
Okay, thank you.
So you have to share your screen. Yes.
Yeah, I'm sharing now. Okay, is it visible now?
Perfectly.
Okay. Okay, so let me start. So, oh, sorry, 1 second. Just give me a moment. I have not connected my tablet. Sorry. Okay, so let me continue where I left off. So by the way, I did not share any notes after the second lecture. There was whatever I said, except Trotter's tridiagonalization technique. I did not write that into the notes, but other things were there already in the earlier notes. I did not do too much last time. So let me continue where I left off. So today I want to do two things. One is continue with this little bit of what I mentioned last time, zeros of orthogonal polynomials. That sort of indicates an idea of why these tridiagonal matrices are kind of conceptually nice and useful. And then I will go to the largest eigenvalue, in particular the n to the minus 2/3 scaling, and say how that comes about. So some of it may spill over to the next lecture also. Okay, so by the way, if somebody did not attend last second lecture, it should still be possible to follow this, because I am going to define what the problem that I'm doing is. So if you attended the first one, then it should be okay. So what is it that we want to do here? I just want to say a little bit about this zeros of these orthogonal polynomials. So let's take, this is all deterministic, but what this has to do with tridiagonal matrices, that's the point. So we start with some measure mu, okay? So it's a probability measure on the real line. I will assume that all moments are finite. All moments are finite. And I also assume that mu does not have finite support. Okay, so if mu has finite support, then I'll say why that is needed. So all moments finite, in which case you can look at 1, x, x square, and so on, the monomials. They are all in L2 of mu. So you can apply Gram-Schmidt to this to orthogonalize them. And get polynomials phi0, phi1, phi2, etc. What are these? So these are polynomials. So polynomials. So these are what are called orthogonal polynomials with respect to mu. To be precise, this is how I am going to normalize it. So phi k will have degree of phi k is exactly k, but I'll make it monic. It's not normalized. Phi k of x looks like x to the k plus some stuff. Okay, so the first coefficient is 1, monic. So it's not normalized in L2, but they are orthogonal. Phi k, phi L, d mu is 0 if k is not equal to L. Okay, so this is what, so this is clear. So if all moments are finite, so reason I assume that the support of mu not finite. If support of mu is finite, L2 of mu will be a finite dimensional space, and there will be only finitely many orthogonal polynomials, really, I mean linearly independent ones. So only finitely many monomials are linearly independent, so you can apply Gram-Schmidt only to that. So let me avoid that case and do this. So from the orthogonality, one can check that then it's a, so this is a fact I will say, it's easy. So let me leave it as it is. So then there exists. So first point that I want to say is this 3-term recurrence. What is the 3-term recurrence? So there exists some numbers an and bn. An is just a real number and bn is a positive number such that phi n plus 1 of x will be x minus an phi n of x plus, sorry, this is usually written minus, so let me write. So here I have minus bn minus 1 squared phi n minus 1 of x. Okay, so this is for n equals 0, 1, and so on. And anything with index minus 1 is 0. So when you write n equals 0, there is a b minus 1 or phi minus 1. They are all 0, that's all. So this is an easy thing to derive. Let me just tell you how. You just take x times phi n of x. That's a polynomial of degree n plus 1. Since phi k has degree exactly k, you can write x phi n of x as a linear combination of phi naught up to phi n plus 1. And then use orthogonality to show that most of the coefficients are actually 0. So you're only left with a coefficient of phi n plus 1 and coefficient of phi n minus 1 and phi n. So that is how one arrives at this. I will not try to derive that, but it is better to write it like this. So this gives me these numbers which form this tridiagonal matrix. Okay, so here is the Jacobi matrix. Here is where the Jacobi matrix enters the picture. So which I denote T is this Jacobi matrix like before, except it's an infinite matrix. And I start indexing with 0. That is more convenient here because polynomials start with degree 0. Sorry, this is not like this. The way I have written is A naught. So there will be a 1 here. P naught square, 1. And so on. Okay, so this is an infinite tridiagonal matrix. And so what these 3-term recurrences here, they can be written like this. So let's also introduce, what I can.
It's 7 o'clock.
So the 3-term recurrence can be just written like this, that if you apply t to this vector, phi naught of x, phi 1 of x, phi 2 of x, you consider this infinite vector and multiply by t. All multiplication is okay because all things have all entries. Each entry is a finite sum. So there is no problem in multiplying t with this vector. What you get is exactly x times the same vector. So in other words, this vector, if we denote capital phi of x, is an eigenvector, formally an eigenvector. With eigenvalue x. Okay, it's just formally this is an infinite matrix and so on. But it is so this is exactly this 3-term recurrence. I just carry x phi n of x to one side and put the other things to the other side. So phi n plus 1 of x plus an phi n of x plus bn minus 1 square phi n minus 1 of x. That's what comes on the left side, and that's equal to x times phi n of x. So that's the idea of this. So this is the way to write it. So what is so this is formally like that, but what is the point? So I want to now consider finite submatrices here. So I want to say a few things first before I get to my question. My question is about zeros of this phi n. Okay, so that's what I will address first. And all this can be applied also to the random tridiagonal matrix that we talked about. But here no randomness is required in what I am discussing. So here let us take Tn to be the top n by n part. So by n part, since we are indexing from 0, this goes from a0 to an minus 1. And on the top, we have 1s. And in the bottom, we have b0 square, bn minus 2 square. By the way, so the difference between this one and the other one, this one is not a symmetric one. But like I indicated in one context last lecture, so any such matrix can be made symmetric very easily. You can conjugate it by a diagonal matrix and make these entries b0, b1, and these entries also b0, b1. In general, you can divide this entry by something, 1, 2 entry, 2, 1 entry by something, and multiply 1, 2 entry by the same thing. And same for all these pairs. So that you can do by conjugating by a diagonal matrix. Therefore, this matrix is conjugate to the one with a0, a1 on the diagonals and symmetric with b0, b1, b2 on the super and subdiagonals. So it's the same thing actually. So eigenvectors will change in a sort of way which we can handle, but this is convenient, that's all. So let Tn be the top n by n part of this. So, and similarly, let phi n, let's restrict the phi n of x, let us say is the top, I take the top n coordinates of phi of x. Okay. So can we say that phi n is an eigenvector of Tn? So what I want to do is I want to take this equation here, t times capital phi of x. So this is true for all x. Capital T times, t times phi of x is x times phi of x. So can we say that, is it true that Tn applying to phi n of x is equal to, so can I get the eigenvectors like this? Of course, it would be ridiculous if the answer is yes, because then you will get infinitely many eigenvalues. That should not be the case. And why does it not work? So if you look at the eigenvalue equation, Tn phi n of x, you look at the first equation. So you get a0 phi 0 plus 1 times phi 1. If n is large, then that is same as what we get here, a0 phi 0 plus phi 1, which will be x times phi 0. So you'll get x times phi 0. So if you write out the eigenvalue equations as n equations, all of them are satisfied except the last one. The last equation, in here, the last equation, that equation which would look like bn minus 1 square of times phi n minus 1 of x plus an, phi n, bn minus 2 square phi n minus 2 of x plus an phi n minus 1 of x plus phi n of x equal to x phi n minus 1 of x. That's what I get here. From here, this is what I get. But here, that extra term, this term is not there because the matrix ends here. There is no 1 to the right of this. So this is an n by n matrix.
Oh, excuse me, should it be an minus 1?
Sorry, which one? Oh, sorry. Yes, you're right. That is an minus 1. So this one is actually n minus 1, phi n minus 1 of x plus phi n. So this extra term is there. So when will this be satisfied? This is satisfied if and only if phi n of x is 0. So in other words, the eigenvalues of Tn are the same as zeros of phi n. And eigenvectors are, so let's give it a name. So let us call it zeta n1, zeta n2, zeta nn. In a moment, I will argue that they are all real numbers. So let's say we put them in that order. So the eigenvectors will be correspondingly phi n of zeta n1. That will be the first eigenvector and so on. And phi n of zeta nn. They will be the corresponding eigenvectors. Okay, so that's clear from here. So why are they actually all real? And so that is actually, one can deduce that from this 3-term recurrence. So let me just indicate how. So look at this 3-term recurrence. So let me quickly say, these are all standard analysis facts. So I am just going over them. So what is from here, actually we can deduce two things. The zeros of, so two statements, let me make two statements and then deduce it from the zeros of Pn are real and interlace with those of phi n minus 1. So in other words, so here is interlace means, so zeta n1 is zeta n2 and so on. So zeta n minus 1, the first root of phi n minus 1 will be somewhere between the first two roots of phi n minus 1. Zeta n minus 1, 2 will be here and so on. And there is zeta n minus 1 and zeta n. So the last root of will be here. Okay, so that's the interlacing part. And if they are interlaced, there have to be n of them actually. So that's the thing. So the interlacing follows from here. So the 3-term recurrence. Inductively, I mean, so why? What is this interlacing? You start with phi naught. Phi naught. So let me just write it like this pictorially. Phi naught. Let me choose. So phi naught. Let's write. Phi naught is actually the polynomial 1. See, phi naught is 1, so it is positive everywhere. So let me write it like this. So it is positive everywhere. So if I write the real line, it is positive everywhere. Next, you go for phi 1. What about phi 1? It will have, it is a linear polynomial, and you can see that it will have one root. So it will be, phi 1 is, what is it? It is polynomial, it is positive beyond a point. And then before that, it is negative. Oops. Okay, so this is, and what we can see from here in this 3-term recurrence is when you look at phi, let's say we have carried over up to a certain point, and so this is for phi 1, and phi 2 will look like this. So it will be positive, then negative, and then positive. So it will look something like this. So etc. Suppose you have proved this. Now when you look at phi 3, what we see here is that, okay, so the point is, just look at this one. So when, suppose you take a 0 of phi n in this equation, you take a 0 of phi n, suppose. If phi n is 0, then phi n plus 1 and phi n minus 1 have opposite signs. Okay. So let's go, what does that mean? So that is the only point to notice, that's all. So at any 0, so here is phi 1, it has a root. And at that point, phi naught and phi 2 have to have opposite signs. So the picture has to look like this. Okay. Now you take a 0 of phi 2. Phi 2 at this 0 of phi 2 here, phi 1 is positive, so phi 2 has to be negative. So it has to be negative somewhere here, like this. Similarly here, this is negative, so it has to be positive here. So when you fill in the picture, you see that the only way it will happen is, okay, so something is, they have the opposite signs.
Positive, not negative.
Which, this is positive, okay, and then this will meet up with this somewhere, and then, but ultimately this has to be positive on this side and negative on the left side, because it's an odd polynomial. So it will look like this. Now you see the zeros of phi3 and phi2 have interlaced, and you can continue like this. Okay, so this is the proof that they have to interlace, and if they have to interlace, all n of them have to be real also. Okay, so this is actually the proof from the three-term recurrence. Now this also tells you that shooting description that I was describing. So this is not strictly required now, but this is actually at the heart of things in a way. So in x infinity equals number of sign changes of this sequence phi naught of x, phi1 of x, phi n minus 1 of x. So how do you see that? So let us say n is 3, and you take an x which is to the right of phi, the last root of phi3 is here, right? So suppose I consider x to the right of it. So if I consider x to the right of it, I draw a line. So this is x, okay?
Sorry,
So
you mean capital phi n in the left, right?
No. The capital phi n is a vector. Small phi n is a polynomial. Capital phi n is sorry, here you mean?
That? What do you mean eigenvalues of the polynomial?
Sorry, Tn, yeah. So number of zeros, and let me say number of zeros of little phi n, which is same as number of eigenvalues of Tn. Yeah. Because we argued that
okay, thank you.
Zeros of Tn also. Okay. So if I take x to the right of all the zeros of phi n, here n is 3, x is to the right, then you see all these intersections are blue, right? It is where it intersects phi naught of x, phi 1 of x, phi 2 of x, phi 3x are all blue. So there is no sign change in this vector. But suppose I bring x to the left and I cross this, I come to below the first root of the largest root of phi 3. Then you see that as you go down this number, phi naught of x, phi 1 of x, phi 2 of x, phi 3 of x, you get one sign change. So there are 3 blues and 1 red. And when you come to the below this root of phi, if x is here, then it changes sign 2 times. It goes blue, blue, red, and blue, and so on. So this is exactly the shooting description of eigenvalues. Okay, so these are some of the things that I just said. But what is it that I want to do with all this? So I just want to ask 2 questions and give a quick answer to them, and they are related to. So there are 2 questions that I wanted to raise and mention these questions. So 1, how are the zeros distributed? And 2 is, how are the zeros interlaced? Okay, what do I mean by how are they distributed? Like we do with the eigenvalues of a random matrix, we can take the empirical distribution or something like that and ask what does it look like? Where is the largest zero of phi n? Where is the smallest zero? Where are they, etc. And similarly, you can ask how are they interlaced? So we know that so phi n has roots like this. So where will be the zero of phi n minus 1 in this? Will it be somewhat halfway, or will it be closer to the right end or closer to the left end or something, or what happens? Okay, so this is the question that I want to mention. And tridiagonal matrices are kind of useful in this. So let me just answer these two questions. Okay. So any questions or comments so far? So these are the two questions that I want to answer. So maybe I write here, I introduce, okay, no, let me go to the next page and then, yeah, so maybe first one I can just write down here. So question one is more or less we have actually done it. So I will make a simplifying assumption, or I'll say what is the part that is simplifying. So just for the lecture, I will assume that ANs are actually 0. Okay, so let me take the ANs to be 0, and BNs we have to assume are going like, let's say, n to the alpha or something like that. So for some alpha greater than equal to 0. Okay, so I will make this assumption. So AN and BN are these coefficients. Okay, so one has to know how these coefficients behave. If you give me the measure mu, then can you figure out? Yes, in principle, yes, one can know what they are like. AN equal to 0 is same as saying the measure is symmetric about the origin actually. Okay, so that is this is a simplifying assumption. Okay, this is just for simplicity. I just want to convey the main point. But Bn is n to the alpha sort of is necessary. I need Bn is kind of regularly varying or something like that. So that is kind of required. So let's make this assumption anyway. So what is the answer to question 1? So question 1 can be very easily answered then. So you look at the ln, which is the, so the thing is the zeros are, the zeros of Pn I denoted by zeta nk, right? It turns out they are actually of the order of Bn. So Bn is what controls the range of this zeros. So they will be sort of from minus Bn to plus Bn. Okay. So roughly that is what this is. So you look at this one. So that is, we are looking at ln is 1 over n delta zeta nk over Bn. So what happens to this empirical measure? That is what would answer the first question. How are the zeros distributed, right? Now this is actually very clean from the tridiagonal matrix. From the, if you just look at it as polynomials, maybe it is not clear how you go about it. But if you use the tridiagonal one and use the method of moments, it becomes kind of clean. So why? Again, let's look at the moments of this. So this is something essentially we have done this, but for the random matrix. So again, our measure will be symmetric. That's why I made this simplifying assumption an is 0. You can write with, so it's only even moments that I need to consider. So let's just look at the even moments of this ln, which is 1 over n. And then I have to take zeta nk over Bn to the power p. So I get 1 over Bn to the power, 2p. Some k equals 1 up to n, zeta nk to the power 2p, right? But since these are the eigenvalues of Tn, so this is the same as trace of Tn raised to the power 2p divided by n times Bn raised to the power 2p. Okay, now we can write it out just like before. You just sum it over all paths. So I will assume that you sort of remember some of the things that I did. So here we get a sum over all Tn of I1, I2 up to Tn of I2p, I1. I have to take all such things, but since our matrix is tridiagonal, only successive ones will, so I2 and I1 have to differ by 1 and so on. So that's what happens. And now you have to take a path which goes in 2p steps. It goes from I1 to I1. So let's say the starting point is k. If I fix the I1 as k, then how many such paths are there? As we argued, I mean, so this is, there are 2p choose p such paths. Since the diagonal entries I have assumed to be 0, you have to go plus minus 1 each time. So there are 2p choose p paths which go up and down. This is not quite correct if k is close to 1 or n, right? But if k is more than p or less than n minus p, then this is true, because the constraint that you should not leave 1 to n will not apply there. I mean, will not make any difference. So that will be the number of paths. But when you are at the location k, all the weights, there will be 2p, out of which p of them are +1 and p of them are -1. Now all the plus ti plus 1s are 1, ti minus 1 are bi square. So all of them being close to k, they will look like bk to the power of 2p. This is how it looks. Now, because of the assumption that, so this is exactly the calculation I had done earlier for that specific matrix that I had. But now you assume bk behaves like k to the alpha. So bk, so this is like k by n to the power of 2 alpha p. Bk by bn will be k by n to the power alpha. So this whole thing looks like, so approximately 1 over n sum of k by n to the power of 2 alpha, sorry, not 2 alpha, it is 2 alpha p. And then there is a 2p choose p outside. Now you can approximate this by an integral. It is the integral of x to the 2 alpha, right? So this is actually, it's integral of x to the 2 alpha. So this looks like 2p choose p. And if you integrate x to the 2 alpha, you can write it as 1 over 1 plus. So maybe I made a mistake here. No. 2 alpha or alpha? Yeah, it's x to the, so 2 no, this is correct. Sorry, 1 plus 2 alpha p. So this is what you get. So the ln, the moments of ln converge to these numbers: 2p choose p, 1 over 2 alpha p, which, so there are special cases when alpha is 0. When alpha is 0, for example, this is true for Chebyshev polynomials. For Chebyshev polynomials, the recurrence coefficients ans are 0 and bns are basically 1. Okay, so in that case, bns are not going, alpha is 0. So in that case, you just get so this you just get 2p choose p as the moments. So which corresponds to the arc sign distribution. And indeed, one can write down explicitly the zeros of the Chebyshev polynomial. They are, you just get some cosine of k over n or something like that. So you get the arc sign distribution. When alpha is something like square root n or square root n minus 1 or so, this corresponds to the Hermite polynomial. So this corresponds to the Hermite polynomials. And in that case, we get what we did before, 2p choose p over p plus 1. These are the Catalan numbers. And this is corresponds to the semicircle. So this is the answer in general. So this is
alpha is not square root. Alpha is 1/2.
Sorry, alpha is half. Alpha is half. Yeah. Thank you. So, yeah, alpha is 1/2. Okay, so that's what happens. In that case, you get Catalan numbers, and that corresponds to semicircle. So in general, you get this. So this is actually, so in, I could not find exactly in Zigo's book the full generality in this theorem. I don't know where it is written, but Kerov attributes this to Zigo. So it is Zigo's theorem for asymptotics of orthogonal polynomials. So zeros of orthogonal polynomials. So you get, for all these cases, you get the answer. So this is how roots behave. And a special case is our random situation also was bk was behaving like square root of k, right? Well, okay, our matrix was kind of reversed. That's all. But otherwise, it's the same. Spectral, I mean, the empirical distribution is the same. So that this corresponds to our tridiagonal random matrix, the second case, Hermite polynomial situation. So that was first thing that I wanted to answer. This pretty much answers this question: how are zeros distributed? By the same method of moments. Next, I want to tell you about how zeros are interlaced. Okay, but before that, if there are any questions, please feel free to interrupt at any time. Okay, so I go now to the interlacing question. How are they interlaced? Okay, so same setting. So we have these orthogonal polynomials. And then there is the tridiagonal matrix and all that. When needed, I won't write it. I'll go back to the previous page when needed. So let us take phi n and phi n minus 1. So just to simplify notation, so let me just use the zeros as u1, u2, un, and the zeros of phi n minus 1 are between v1, v2, v3, vn minus 1. Okay, so in my earlier notation, uk is zeta nk and vk is zeta n minus 1k. Okay, so what we want to understand is the interlacing of these two things. So them together. So it was, I think, Keo who probably first considered this at all, this kind of stuff. This interlacing occurs in many places. I'll mention a little bit later. But so what is a thing that captures this whole thing? So we can introduce this measure, which is not a probability measure. K equals 1 up to n. Delta uk. You put masses 1 at the uk's and masses minus 1 at the vk's. Okay, so this is called an interlacing measure. No need to define it in general.
You missed delta in the second sum.
Oh, yes. Sorry. Yeah, delta. So the measure, it puts mass 1 by n. Sorry, no 1 by n. So there is no scaling. That is so that is what we want to emphasize. It's just the counting measure at uk's minus counting measure at vk's. But it is sort of well, because of the interlacing, it is well controlled. For example, if you look at tau n of, if you look at the cumulative distribution function of this. So if you look at tau n from minus infinity to x, okay, it is always between 0 and 1. So the CDF of this measure is also like a CDF of a probability measure. It's between minus 0 and 1. Same with tau x of x to infinity. Is also between 0 and 1. That's really the property of interlacing measure, that such a thing Keo calls interlacing measures. Okay, also called, so there's another term he uses, Rayleigh measures. I'm not too sure where and what Rayleigh did in this, but this is the thing. So first of all, okay, this clearly tau n captures both the roots of Pn and Pn minus 1. That is clear. But what it says about interlacing is not clear. Let's not worry about that for a moment. Let's just apply method of moments to this one. What do you get if I just blindly apply the method of moments to this? X to the 2p d tau n of x. What do you get? Well, first of all, you get summation uk to the power 2p minus summation vk to the power 2p. That's what we get, right? But what is summation uk to the power 2p? Let's go back. UKs are zeros of phi n, which are same as eigenvalues of this Tn. And phi n minus 1 similarly corresponds to Tn minus 1. Tn is the top n by n part. Tn minus 1 is the matrix got from Tn by cutting off the last row and last column, right? So this is nothing but, there is no 1 by n here, notice. So this is trace of Tn to the power 2p minus trace of Tn minus 1 to the power 2p. Okay, what will that give me? Well, they are both submatrices of that big matrix T. So you get all such paths, T I1, I2, T I 2p I1. Again, I am not considering the odd ones, which are going to be 0, because I keep assuming, I stick to the assumption that an is 0 and bn is like n to the alpha. Okay. Okay, maybe I should have done one thing. So I should have divided everything by bn. Okay, so let me scale it. Sorry about this, I should have said it earlier. So to see the picture, because we know the roots are in minus bn kind of by the previous one, we know that the zeros are like, so after dividing by bn, we have a limit. So it makes sense to consider these things after scaling by bn. Both of them I scale by bn. So what we get here is, there is a 1 over bn to the power 2p multiplying this whole thing. Okay, but the point to notice here is what are these I1, I2, I2p, I1. Okay, so they are coming from I1 up to I2p have to be between 1 and n. That much is clear. So it is a path which goes, but we are subtracting tn minus 1 to the 2p. So what we need is that the only things that remain are where the at least one of them is equal to n. Okay, so this is what the sum is over all paths which actually hit the level n. So if you are thinking of the integers, so if the path is entirely contained in 0 to n minus 1, that will also occur in this one and it will get subtracted. It cancels. Therefore, what remains is only these things. Okay. So what does that look like? So when the maximum is, so all these paths, they touch, they don't have to start at n. They can start at n minus 1 or n minus 2 or n minus p also. But they have to hit n and that will be the maximum. They should not go beyond n because then also it won't occur. So what will this look like? First of all these t, I1, I2, etc., they are somewhere in close to n, right? Within n minus p to n. So this will look approximately, all the weights will look like bn to the 2p over bn to the 2p. So that cancels. So all the weights t of I1, I2 over bn is approximately 1. So the weights cancel. So it is a question of number of walks of length 2p that return, okay, okay, from k to k that stay in 1 to n and hit n. Each such path will contribute a 1 to this. So how many walks are there of length 2p that start somewhere from somewhere to somewhere, but they have length 2p, but they have to hit n. So how many are there? See, that is actually easy. So I say it is just 2p choose p. So think of any walk like that. Let's say you start the walk at 0 and you consider any walk. Let us say it looks like this. So this is a walk that starts at 0 to 0. If I consider all such things, there are 2p choose p of them. And there is exactly one way to push it up so that the maximum hits n, right? So the maximum, it can hit many times, doesn't matter, but there is only one way to push it up so that the maximum hits n. So this number is exactly 2p choose p. So we get this nice point that tau n converges to, and these are the moments of the arc sign. So it converges to arc sign. So this measure, the interlaced measure, converges to arc sign. So this is directly from the method of moments. So, but what does that even mean? What is that telling about the zeros? What did I learn about the roots? By the way, are there any questions? Is it okay? I mean, so this calculation, I hope is clear. It's just moments.
Yeah, I have a question. You showed it under this assumption, but does it hold in general?
Yes, yes. So there is a more general thing. So if ANs are small, okay. So let me just remark on the side. So what is the generality? Here you see it's, by the way, one remark is that this is always arcsign, unlike the previous one, where it depends on that alpha. Okay, so the answer depended on the alpha. Now it doesn't depend on the alpha actually. It is always that, it is always the arcsign. So this result is sort of more universal than the previous one. But what is the optimal conditions under which Keough proved it? Keough proved it under the condition that Bn over Bn plus 1 goes to 1 and An minus 1 over Bn goes to 0. Okay. So if
and whose result is this? Do you know?
So yeah, I will mention. This is all Keough. So he was your, I don't know, city person long time ago, probably before you were there. So he was, I guess, in St. Petersburg. And,
yes.
Yeah. So his papers are really beautiful, actually. So this he has many papers on interlacing measures. So this is one of them, suppression of roots of orthogonal polynomials. He proved it under this condition. See, but one point will be that if it is like this, if I assume that An is little of Bn, that is a stronger assumption than this, then you can more or less do it exactly the way I did it. But if An can be of the same order as Bn, then you have to also do a centering. It won't be UK over Bn, you have to do a centering also. Okay, that is the other part. So there will be a centering required. Otherwise, if you assume An is smaller than Bn in this sense, then you don't need a centering. Okay. So, but I haven't yet said what it says about. Okay, that answers your question, right, Dima? So this is the.
Yes, exactly. Thank you.
Yeah, this is the most general that I know. So what are we saying from all this? So for interpreting this, Keough introduced this very important diagram. So let me say, so we have already produced the result. Now we have to understand what it is saying. Okay, so from this point of view, so there is a diagram that associated to tau n. Okay, so what is the diagram associated to tau n? So let's write here. Oops. Yeah, drawing is more painful on this. Okay, so let us say we have. So let us say our zeros. So let us say this is U1, and then there is V1, and then there is U2, and maybe there is V2, and U3, and so on up to UN is here, and Vn minus 1 is here. So what Keough introduces is this diagram. Omega n is a function on Rn. How does it look? It is piecewise linear, okay, and it has slopes plus minus 1. So omega n dash. So I will write in pictures. I will not write. So omega n will be piecewise linear, and it will have slopes which are plus or minus 1. Between a cross and this, it will have a slope of plus 1. Between a circle and a cross, it will have a slope of minus 1. Okay. So it is like this. The slopes are like this, and before the first cross, it will have a slope of minus 1. So after the last cross also, it will, after that, it will have a slope of plus 1 from up to this point, and before that, it is minus 1, and like this. Okay, so omega n dash of x is 1 or minus 1, 1 on UK to VK, sort of, okay, and also UN to infinity. Minus 1 on VK to UK plus 1, but also on the first interval, minus infinity to U1. Okay, so this is how he defines, this defines the derivative of omega n. But you have to also do one thing. So then there is a constant left in defining omega n. So you put the condition that you lift the diagram up so that omega n is exactly mod x for large X. In other words, you take this diagram, you continue this. This first curve, first line, you continue this downwards. And this last line, you continue downwards. So you just place your axis, real x-axis here. So this is how you see the picture. Okay, you lift it up exactly so that it looks like this. So in between, it will look something like this. So this is the picture. Okay, so this picture now looks like the graph of a function omega n. This is the graph of omega n, what I have drawn here. Okay, it is a Lipschitz function with Lipschitz constant 1, and all the slopes are plus minus 1. So this is what the diagram associated to tau n is. Clearly, omega, what is it? Another interpretation, Kerov never says this, but one way to think of omega n is like it is like if you are Riesz potential of tau n. So what do I mean by Riesz potential of tau n? What I mean is that if you take the Laplacian of omega n, which in the one dimension is just omega n double dash, okay, second derivative, is actually, what is omega n dash? It is minus 1 here and then plus 1 here. So it changes from minus 1 to plus 1. So it has a mass of 2. Okay, half of omega n double dash is actually tau n in the distributional sense. So if you see half of omega n dash, it is minus 1 here and jumps to plus 1. Or half of omega n dash will jump from minus half to plus half. So its derivative is delta at u1. Here it is the other direction at v1 minus delta v1 plus delta u2 minus delta v2 and so on. So in that sense, it is if in Riesz potential means if you are in 2 dimensions and you want to take a measure, if you have delta xk, the Riesz potential will be summation log mod z minus xk, because log is the Green's function in 2 dimensions. What is Green's function in 1 dimension? It is mod x. Mod x is the one whose whose Laplacian or second derivative is 1, or half mod x is the one whose Laplacian is plus 1. So in that sense, this is actually the sum of all the, you can write it exactly like this, summation. So you can write this as summation x minus uk minus summation x minus vk. That is exactly what this thing is. Okay, so that is another way to write this omega n of x. So this is, in that sense, this omega n has all the information you want about tau n. But it is more easy to interpret. What does it say about? So from this, Kerov deduces this part I will not explain. This is more of a sort of analysis that from this, it turns out that omega n converges, not omega n. Okay, so there is a scaling required, right? So in tau n is, yeah, so sorry, sorry, I made a mistake. Sorry about that. Yeah, sorry, slight confusion. Tau n is with the scaled zeros, scaled by bn. So this omega n double dash is not tau n actually. So that's not correct. So let me introduce a notation. So if I do the same with the scaled ones, okay. So if I do all this with the scaled zeros, you do everything with the scaled zeros. That is what I will call omega n. Okay, but all the things that I said roughly remain the same, but this statement actually becomes correct now because I am working with the scaled zeros. So omega n double dash is gives you tau n. So the fact that tau n converges to arcsine, from that he deduces that omega n itself converges to a limit shape which is called capital omega uniformly Okay, and what is this omega? Omega of t, there is an explicit formula. So let me just copy it because it's, yeah, so it is omega n is 2 over pi t times arc sine of, it's not important to remember any of this, but let me just write it, square root of 4 minus t square if mod t is less than equal to 2 and mod t if mod t is bigger than 2. So what it looks like is like this. So beyond minus 2 to 2, it is like mod t. Okay, so this is minus 2 and this is 2. And between that, there is a certain shape which looks like this. So this is t, this is omega of t. Okay, so and this is so that this, if you see this, yeah, this looks like this is the limit of that picture. That's the claim. Okay, after the scaling of UKs by BN. So this, okay, so you can sort of believe what is the property. Omega is related to arc sine exactly like omega double dash of t will be the arc sine density. So this form, it is not familiar, t times arc sine of all this, but omega double dash. So just as, okay, maybe it is half omega double dash. Okay, I don't know what. So I may have messed up the scales here. Maybe half omega double dash is the arc sine density. But so basically, this is believable that omega n double dash converges to semi arc sine will imply that this omega n converges to omega. It requires a proof, and this convergence is uniform. So, but this one is easier to interpret. What is it saying about the interlacing of roots? So this picture, if you see, you see this, right? So let me write this again, this picture. What is this picture telling us, this diagram telling us about the roots? Suppose on some range, I have the roots of some UK plus 1, UK plus 2, etc. All, if you want to think of it as the scaled ones or the unscaled ones. Suppose your suppose your VKs are sort of midway between the two. Then the diagram looks like this. It will be going down with slope 1, going up with slope 1, then going down with slope 1, going up with slope 1, going down with slope 1, going up with slope 1. So overall on this, it remains flat. It's not either going up or coming down, because over UK to UK plus 1, since it is midway, it goes equally plus, minus and plus. So it sort of stays flat. Whereas if the spacing was not like that, if UK, I have UK plus 1, let us say our interlaced root is always 3/4 of the way from UK and 1/4 of the way from UK plus 1. So then it goes down for 3/4 of the way, goes up only 1/4 of the way, and then goes down for 3/4 of the way and goes up for 1/4 of the way, etc. So overall, the graph has a slope downwards. So the slope of this diagram is telling you whether the roots, the interlaced phi n minus 1 roots are close to the right side or the left side. When they are close to the left side, the graph is increasing. When they are close to the right side, the graph is decreasing. Okay, did I make a mess here? Right. So this is correct. Sorry. When they are close to the right side, the graph is decreasing. When they are close to the left side, they are increasing. So this tells you, if you look at this capital omega, which has a decreasing slope here, that means here the interlaced roots are sticking close to the left side. You can say in terms of the slope here. Whereas on the left side, they are sticking close to the right side. So this is a sort of very coarse version of bulk. I mean, what people study in randomness and so on is one wants to study the gaps between roots and so on. This is a kind of coarse way of not, you can't say anything about very specific interval. It is an average sense in which this spacing is dictated by this shape capital omega. So that is the result of Kerov. Okay. Any questions about this interpretation? So with that interpretation, we can say that this theorem that tau n converges to arc sine and the omega n converges to capital omega, they are interlinked theorems. They answer the question about interlacing in this average coarse sense. Okay. So that's the final answer. This same shape Kerov showed in many papers. So all papers I have read have this formula of capital omega in his, all papers of Kerov that I have read more or less have this. So he has a lot of papers on. So the first time this came, this makes me to allow just mention a digression, but link with something is when they considered what was the longest increasing subsequence problem. So I will not describe that problem, but what it reduced to was to consider random Venn diagrams from Plancherel distribution. So the random Young diagram is like this. So it is written like this. So Young diagram looks like this. It's a diagram of a partition. So you put a number of boxes. It consists of boxes like this. And then the number of boxes will decrease as you go up to the right. It may have like this. So this is a picture of a Young diagram. You place it in this 45 degree. And then you see the thing is, so they were studying a particular probability distribution on these types of diagrams with n boxes. Okay, so that distribution is called the Plancherel distribution. It is the most natural distribution on diagrams with n boxes in some sense. So there you have this. How do you study this? Basically, the shape of the diagram is given by this. And this is exactly a diagram of the type I wrote. There it has slopes -1, +1, -1, +1, -1, +1, -1, +1. Except the difference from the previous one was here we came from the side of these points. And this omega n was a tool we introduced to understand that that signed measure tau n. Here somehow the diagram is the first thing that you come across. That's what you want to study. And local minima and local maxima correspond to the interlaced points. So the local minima are interlaced with the local maxima. Okay. So, but what this is the first place where this whole thing appeared actually in the work of Kerov and Varshik. That is where they showed that when you take this Young diagram from this Plancherel distribution and scale it appropriately, when you have n boxes, you have to scale by square root n, then you get this limit shape, the exact same limit shape omega. In all sorts of interlaced situations, you tend to get this limit shape. So this is there in many papers of Kerov. Okay, so that finishes pretty much what I wanted to say about this part. It took much longer than I intended, but it's okay, I guess. Yeah, any questions about this? So again, this, by the way, this also works for random situations. What about random situations? Another situation where this arises is even if you don't care about tridiagonal matrix, you take a Wigner matrix. So which means that Aij is Aj and Aij I less than equal to j are IID mean 0, and let's say variance 1 over n. I suppose I have scaled it so that the variance is 1 over n. Then so this has some eigenvalues. So lambda 1, lambda n. So you have these eigenvalues. What are they interlaced with? So you take a random projection. So P is a random hyperplane. Hyperplane, I mean n-1 dimensional subspace. So random hyperplane, like Zakar was doing the other day, you pick a Gaussian vector and then pick a hyperplane orthogonal to that. That's what it is. And you look at the contraction of A to this hyperplane. Let's say this is B. Okay. So then you get some mu1, mu2, mu n-1. They are interlaced actually. So the eigenvalues of this are mu1, mu2, mu n-1. They are interlaced with the eigenvalues of A, which are lambda1 up to lambda n, and exactly the same limit shape holds. So if you form this tau n, which is the summation delta lambda k minus summation delta mu k, then it converges to the arc sign, and the corresponding diagrams converge to this same shape, the Virchow-Kirchhoff shape, capital omega. Yeah, so this is also, this arises in many situations of interlacing. Okay, so that completes everything I wanted to say about these things. So yeah, okay. So people have now, I think, with all these recent works of Erdős and Yao and so on, and there was a paper of Tao and Wu, this interlaced business is studied maybe in a much finer way, where you look at it in a finer fashion of looking at an individual one and so on. I'm not too sure what the results are. So, okay. So let me, if there are any questions, this is a good time to ask, because I now completely go to a new topic, which is the largest point in the quadratic log gas, the n to the minus 2/3 scaling and all that. Okay. Any questions? Okay. So if not, then let me continue. If I lost anyone, then this is a good time one can come back. There is absolutely nothing that you need to know except the tridiagonal matrix that I introduced in the first this, which I just quickly recall. So what I want to understand is this beta quadratic log gas. And so I'm back to studying that. We saw some properties of it. So in the very first lecture, I said what are the questions that we want to study about it. When we look at a beta log gas like this in general potential, where are the particles? What is the overall distribution? What are the gaps like at the edge, in the bulk? I won't say anything about bulk. We'll study the edge, which is kind of more interesting also. And I understand it better. But we first stick to the quadratic log gas. So the quadratic log gas has this density. So we have n particles with...
It's 8 o'clock.
lambda I minus lambda j to the power beta, e to the minus beta n summation lambda I square. I equals 1 to n. Okay, so this is the quadratic beta log gas. Okay, I think I had a 4 here. Beta n by 4 summation lambda I square. And these are the eigenvalues of this T beta or Tn beta. I don't know what I got. So 1 by square root beta n. Where AK is normal 0, 2, BK squares, chi square with beta times n minus k and all independent. Okay, so this was the tridiagonal matrix. The eigenvalues of T beta n have exactly this distribution. This is something I said in the first lecture. Is there a question? Okay, so did somebody ask a question? I can't hear. I hear some noise, but I don't know what it is. Okay, so what are we now interested in? So what we showed that lambda n So lambda n converges to 2 in probability. Okay, so this I did in the first one. Okay, since I didn't say it then, so let's look at the largest eigenvalue. We showed that the range of the thing is in -2 to 2. Okay, so in that sense, lambda n is not much larger than 2. So this shows lambda n bigger than 2 plus epsilon, that probability goes to 0. But we also showed Wigner's semicircle law, which shows that the empirical distribution goes all the way from -2 to 2. So probability lambda n is less than 2 minus epsilon is also going to 0, because we expect a positive fraction of roots between 2 minus epsilon to 2 plus epsilon. With that, we actually have proved this. I just write this. I should write lambda n1, lambda n2, etc. But I'll just write lambda 1 less than lambda n. We have shown this. We have shown lambda n converges in probability to 2. So question here that I want to answer is, how far is lambda n from 2? Okay. So the answer, so what are we going to tell? Since I have only a few 5-6 minutes, so let me just mention the answers and what we are going to do next time. So lambda n minus 2, so the answer turns out to be that lambda n minus 2 is of the order of n to the minus 2/3. We will show this. So this I gave a heuristic last time from the semicircle density, that if I want a mass of 1 over n in the semicircle, then the amount that I have to go to epsilon n will be of the order of n to the minus 2/3. Okay, when I write this wiggle here, this one, I mean up to constants, it is like that. So lambda n minus 2 is of this order. But what is the, but in fact, we will show much more precise things. So we will, using the tridiagonal, I want to do something very precise to show the power of this tridiagonal approach. So we will show, in fact, very sharp estimates, which will, so of the following type. We needed it for a purpose, but we can ask the upper tail. For example, what is lambda n probability lambda n bigger than 2 plus t times n to the minus 2/3. We know that lambda n minus 2 is of the order of n to the minus 2/3. What is the chance that it is more than that? By a big constant t, okay, by a big factor of t. This is as t goes to infinity. So we will show that this is, so let me write equals. So this will be like e to the minus, it is actually e to the minus, so the constant, you will even do it with the constants. 2/3 beta t to the power 3/2. Okay, so it's not equal. What I mean is here there is a factor 1 plus little o of 1. E to the minus as t goes to infinity, but t should not be too large. I mean, you know, for example, in the case of sums of independent random variables, when I look at Sn by square root n, this is very much to be compared with that situation. For analogy, let me just say this. When we look at Sn is, let us say, sums of independent Bernoullis, and we know that Sn by root n converges to Gaussian. And Gaussian tails are like, I can say that they are like e to the minus t square by 2. So what can we say about probability Sn by root n bigger than t? That also is like e to the minus t squared by 2, provided, of course, this is for t going to infinity, but not too fast. T should be kind of smaller than square root n, because once you take t as large as square root n, the large deviation regime kicks in, and it's no longer going to go like e to the minus t square, but just e to the minus n times. It won't, if you, even if you take n to the 0.51, this will, t square will not come. You will just get e to the minus n. So similar thing here. So we have to take t little o of n to the 2/3. We cannot, if you go beyond that, it goes into maybe the large deviation. You can call it large deviation regime. So this is on the right side. But one of the interesting features of this is that lambda n on the other side, the lower tail behaves actually a bit differently. I mean, very differently. So the scaling is the same on both sides, but this behaves like e to the minus, again, 1 plus little o of 1. Everything is as n goes to infinity. Here it is like beta divided by 24. And the tail of in t is t power 3. Again, as t goes to infinity and t is little o of n to the 2/3. Okay, so this tail on the two sides are very different. And what is the reason for that? So this is what I would like to do next time. So just to preview, I will indicate proofs of this, not everything. Maybe I will prove one side of this, upper bound in both sides. Maybe that's what I probably will do, or maybe lower bound on one side, upper bound on another side, something like that. I will indicate a couple of proofs of this. Proofs of a couple of, there are really 4 estimates here. Upper bound for this upper tail, lower bound for the upper tail, and upper bound for lower tail, and lower bound for lower tail. So I will do maybe 2 of those. But this interesting feature of t to the 3/2 and t cube, this is previewing, and these constants are optimal, by the way. 2 by 3 beta and beta by 24 are absolutely the right things, in the following sense that here, let me just recall, this is the result of Ramirez, Ryder, and Virak, and extending the result of Tracy and Bidom. That if you look at lambda n minus 2 and multiplied by n to the 2/3, thus converges in distribution to a distribution called Tracy-Vidom beta. Okay, Tracy-Vidom only defined Tracy-Vidom for beta equals 2 and 1. But the tails of this Tracy-Vidom distribution bigger than t is like e to the minus, in the tail, it's not equal to, it is in the tail, in the right tail, it is like e to the minus 2 by 3 beta t to the 3/2. And the left tail is like e to the minus beta by 12 t cube. Okay, so this is sort of already, this results at the finite level are stronger than saying this in the limit, and they are already telling you, kind of giving you a preview of the Tracy-Vidom distribution. Okay, so the tails are captured in these estimates. And why is the cost higher on one side and the other? There is a nice explanation by energy for this. So there are papers of physicists like Satya Majumdar and Gregory Sher and so on, where they exploit this a lot. These methods cannot be made rigorous, actually, to my understanding. The point is, so the eigenvalues are distributed according to semicircle. Okay, I have to stop in it's already time, but the cost of going excess on this side and excess on this side are different. When you want to lambda n to go up, you can just pluck one eigenvalue and push it up, that costs you. But when you want to push an go to 2 minus something, you have to push all these eigenvalues to the left. And that is the cost, which costs higher here at t cube, whereas here at t to the 3/2. Okay, let me stop there and continue next week. Next lecture, I will do this thing.
Okay, thank you very much, Manju. Please ask your questions.
Yeah, thank you very much. Maybe a short one. The reason we're looking into quadratic case is just for the sake of simplicity, or we can do the same thing for even polynomial potentials, or?
So this was first done for the quadratic one, because these are independent. That is the thing. So when you take a general V, then we can make a tridiagonal matrix whose density is like this. So let's say V of t is t to the 4, V of x is x to the 4. You get a distribution on tridiagonal matrices whose eigenvalues has this distribution. But the entries are not independent and proofs are complicated. But it has been proved now. I mean, so this is we have proved it for uniformly convex and some assumptions on V, but polynomial, uniformly convex, etc. So under that, we can analyze this, but it is basically what this paper of Ramirez, Ryder, and Virag did, which is what I wrote as RRV. They basically reduce the Tracy-Widom limit to central limit theorem, really. So really there is, and so in some sense, all limit theorems are central limit theorem. So there is a central limit theorem you have to show for entries, which implies this convergence.
Mm-hmm.
And what remained was to take this complicated density of tridiagonal matrices here and show that central limit theorem. That is difficult because it's not independent random variables. So that complicates. But it has been done. There are still open questions in that on those lines, though.
Thank you very much. Got it.
More questions? Okay, Manju, it was really very, very interesting for me. I have many new things. For example, I knew about this Vershikerov's result, but I am ashamed to confess that it is my first time when I heard about the Kerov's result, and it is really looks very fantastic. Thank you very much. I really enjoyed it.
Thank you. Thank you.
Okay, and we are meeting in 17 minutes. Now we are having a break.